Hi again. So I'm going through a series of videos here where I'm trying to deal with some questions that a student emailed to me. Once again, I think it's really great that someone's doing that, and it's good for all of the rest of you because you get me making these videos. So what I want to talk about now is the normal approximation to various distributions. And so I want to maybe say a couple of things. I want to say, why do you need a normal approximation? When does it work? And how to do it. Okay, so those are the three things I want to talk about. So let me write this down. So the three questions: why, when, and how. Those are the questions I hope to answer today. So as to the why you need a normal approximation, why does, now I don't even remember what I was going to say with the why, when, and how. Anyway, why do you need it? And so in our previous video, we talked about using using the binomial formula, and we saw that you can figure out the probability of getting exactly three heads if you flip a coin 20 times, for example, right? And you use this little formula called the binomial formula. Let's imagine what the situation you'd be faced in is if you have a question like this. So if you flip a fair coin, let's say 100 times, okay? And so you'd probably expect somewhere around 50 of those flips to be heads, let's say. So let's try to find the probability that you got significantly more than 50. Let's say 60 or more. So what's the probability of getting 60 or more heads? Now you could do this using the binomial formula. Here's what it would look like. So you'd say, okay, what you're going to have to basically do is you're going to say, oh, okay, I'll find the probability of getting exactly 60, and then I'll find the probability of getting 61 and 62, and I'll add them all up. All right? So it would be 100 choose 60 times 0.5 to the 60 times 0.5, so this probability of head, this probability of tail to the 40. But that's just the probability of getting exactly 60. So then you have to say the probability of getting 61, so that's 100 to 60 times 0.5 to the 61 times 0.5 to the 39. And you keep on going like that till you actually get to all 100 of them are heads, which is another thing that could happen, right? So plus 99 choose 60, 100 choose 99. 100 choose 99 times 0.5 to the 99 times 0.5 to the 1. And then finally plus 100 choose 100, which is 1 times 0.5 to the 100 times 0.5 to the 0, but I'll leave that off because 0.5 to the 0 is 1. So, but you're adding up, what is it, 41, you're computing 41 things and adding them up. That's a lot of work, right? And even though a computer could do that easily, we could construct problems that a computer couldn't do easily. But there'd just be too many computations. So what do you do? Because, this is what we know how to do, right? So what we're going to do is, so that's why you need a normal approximation is, or some kind of approximation, you need to do something about the case where you've got a lot of different separate cases to work out. Okay? So now let's talk about how you use a normal approximation and what it is and why it works. So the normal approximation basically takes advantage of something called the central limit theorem. And what is the central limit theorem? Well, I'm just going to quote from the text here. The central limit theorem that says when you draw at random with replacement from a box, the probability histogram for the sum will follow a normal curve, whatever the original histogram was. So, when drawing repeatedly from a box, the probability histogram basically behaves like a normal distribution. For the sum, I missed that. It's really important. The histogram for the sum. That's super important. It's not the histogram of the original data that you get that follows it. The histogram for the sum. So that's a little bit of an interesting concept. So let me explain what I mean by that. Okay. So if I have a box that looks like this, I have a box that has a 0 in it, a 1 ticket, and a 4 ticket in it. And I draw one at a time. Well, the histogram, even if I draw zillions of times, but I just plot them, the data as it comes, the histogram is going to end up looking like this. It's going to be, there's going to be a blip around 0, a blip around 1, and then a blip around, so that's 1 there, and then 2 there, 2 there, and a blip around there. That's what the probability histogram is going to look like. No matter how many I draw, if I'm just writing down the numbers as I draw them, and then just using that to populate a histogram, something like that, you know, and I just go on, it'll just keep looking like that. It'll look essentially like that. You know, it may vary a bit, but it'll look like that. Okay? So that's not what the central limit theorem means. It doesn't mean that if you start just drawing over and over again, that this will somehow start looking normal. So what does it mean? What will look normal? So this is drawing one at a time. Okay, well, what if I draw them two at a time with replacement? Okay, so what I do is instead of drawing them singles, I draw two and I add the two scores. Actually, that's a little hard to see what will happen. I'll show you how I would figure it out. I don't think that this textbook expects you to be able to figure it out, but I'll show you how I would. I'd say, well, just like the dice example I did in another tape, there's three equally likely outcomes, 0, 1, and 4, for each of them. And so the sum of the two will be either 0, 1, 4. So these are sums here. So what I'm doing is I'm saying, okay, I draw once and then I draw again. If I draw both zeros, I get a 0. If I draw 0 and 1, I get a 1. So this is going to be a 1, 2, but this is going to be a 2. This is going to be a 5, and this is going to be a 4, and this is going to be a 5, and this is going to be an 8. So now there's a bunch of different possible sums I could get. I could get 0 with a probability of 1 out of 9. There's 9 possibilities. So the histogram is going to look something like this. 0 will be 1 out of 9 chance. 1 will be 2 out of 9 chance. 2 will be 1 out of 9 again. So there's only 1, 2 there. 3 is still 0, but 4 is going to be 2 out of 9 again. 5 will be 2 out of 9. And then 6, 7, and 8 will be 1 out of 9 chance. So the histogram is going to look something like that for a sum of 2. Now it's going to get pretty complicated to get 3 and 4 and 5, but what the central limit theorem is saying is that the more, as you sum more at a time, the histogram of the sums, not of the original thing, starts to look normal. That is what's going on with the central limit theorem. And you can even say more than that. You can say what the mean is. The mean, or I think we call that the expected value in this class. The expected value for the sum will be the number of things you added up times the original expected value. What was the original expected value here? It's the average of 0, 1, and 4, right? So the original expected value was 5 divided by 3. That means the expected value for this one is going to be twice that, because I'm drawing 2 at a time. And so if I draw, say, 100 at a time, let's say this was 100 at a time, the expected value would be 500 over 6. So it's the expected value equals the number of draws times the original expected value. And the standard deviation will be the original standard deviation divided by the square root of the number of draws. So I'm going to write that down. I think I should write all that down here. In fact, I think I probably need to take a break. Yeah, I do. So I'll take a break and then I'll talk about how to do the normal approximations.